You can't see a single atom. You can't see an electron. Not with your eyes, not even with the best light microscope ever made. It's not a matter of making the lenses stronger. It's a fundamental problem. The things we want to see are smaller than the thing we used to see with. What does it mean to see something? It means light bounces off that thing and into your eye. Your eye's lens focuses that light onto your retina, your brain processes the signals and creates an image. So, seeing is all about bouncing light. Light travels in waves. Think of waves in a pond. If you throw a big beach ball into the pond, the waves will bounce off it. You can tell the beach ball is there just by looking at how the waves change shape around it. The waves reflect its size and position. Now imagine you throw a tiny pebble into the pond. The waves, which might be a foot apart, just wash right over the pebble. They don't really change. The pebble is too small to affect the big waves in any meaningful way. From a distance, just by looking at the waves, you'd have no idea the pebble was even there. This is the problem with seeing very small things. The waves of visible light are too big. A single atom is like the tiny pebble. A wave of light is like the big pond wave. The light wave just sort of washes over the atom. It doesn't bounce off cleanly. It can't resolve the atom. It can't bring back any useful information about it. The size of a light wave, its wavelength, sets a hard limit on what we can see. The shortest wavelength of light we can see is violet light. Its waves are about 400 nanometers long. An atom is less than a single nanometer across, so you're trying to measure something less than a nanometer wide using a ruler where the marks are 400 nanometers apart. No, it just doesn't work. You can't see anything smaller than the wavelength of the light you're using. This is a basic rule of physics. So for hundreds of years, that was that. We could see cells, we could see bacteria, but the world inside the atom, and even the world of large molecules, was invisible. To see smaller things, we needed something with a smaller wave. We needed to throw something different at the pebble. The breakthrough came from a strange idea in physics. The idea was that everything has a wave. Not just light, even particles, like electrons, could act like waves, and the best part was that you could control the wavelength of an electron. By speeding it up, you can make its wavelength incredibly small. Much smaller than the wavelength of visible light. This was the key. If electrons have tiny wavelengths, maybe we can use them to see tiny things. Maybe we can build an electron microscope. This isn't seeing with your eyes. You can't see an electron. So the process is indirect. We're not using our eyes to look through a lens. We're using a machine to detect how electrons interact with a sample, and then using a computer to turn that information into a picture we can understand. There are a couple of main ways this works. The first is called a transmission electron microscope, or TEM. The name tells you how it works. It transmits electrons through the object. First, you need a source of electrons. This is usually a hot filament, like the one in an old light bulb that boils electrons off a piece of metal. Then, you use powerful magnetic fields to grab those electrons and accelerate them. You shoot them down a long tube. Magnets are used instead of glass lenses. A magnetic field can bend the path of a moving electron, just like a glass lens bends the path of light. So you have magnetic lenses that focus the beam of electrons into a tight, precise stream. The whole tube has to be in a near-perfect vacuum. If there were air molecules inside, the electrons would just crash into them and scatter all over the place. The beam would be useless. Then you place your sample in the path of the beam. Here's the catch. The electrons have to go through the sample. That means your sample has to be unbelievably thin. We're talking slices just a few atoms thick. Preparing a sample for a TEM is an art form in itself. You might embed a biological specimen in plastic, and then use a diamond knife to shave off slices thinner than a soap bubble film. So, the beam of electrons flies through this ultra-thin slice. What happens next is what creates the image. Some parts of the sample are denser than others. A cell's nucleus is dense, the cell wall is dense. The empty space in between is not. Where the sample is dense, more electrons get scattered or blocked. They don't make it through to the other side. Where the sample is thin and not dense, more electrons pass through easily. At the bottom of the microscope, there is a detector. It's like a digital camera sensor, but it detects electrons instead of light. Where many electrons hit the detector, the computer screen shows a bright spot. Where few electrons hit the detector because they were blocked by a dense part of the sample, the computer screen shows a dark spot. What you get is essentially a shadow picture. It's a 2D projection of your 3D sample slice. It's incredibly detailed. You can see the internal structures of a cell, you can see viruses. You can even, with the most powerful TMs, see the arrangement of individual atoms in a crystal, where the columns of atoms create a repeating pattern of light and dark. You are seeing the shadow cast by atoms in a beam of electrons. It's black and white, but it's a direct look at a world far beyond the reach of light. But what if you can't slice your sample that thin? What if you want to see the surface of something, not its insides? What if you want to see a bug's eye or the texture of a piece of metal? For that, you use a different kind of electron microscope. This one is called a scanning electron microscope, or SEM. Again, the name gives it away. It scans. It doesn't shoot a broad beam through the sample. Instead, it focuses the electron beam into a very fine point, like the tip of a pencil. And then it scans that point back and forth across the surface of the sample, line by line, like an old television set drawing a picture. The sample doesn't need to be sliced thin for an SEM. It just needs to be coated in a very thin layer of metal, like gold. This is because the sample needs to conduct electricity to work properly. So, as the focused beam of electrons hits a spot on the sample's surface, it knocks other electrons loose from the sample itself. These are called secondary electrons. A detector inside the microscope collects these secondary electrons. The number of electrons that get knocked loose depends on the shape of the surface at that exact spot. If the beam hits a flat part of the surface, a certain number of electrons are knocked loose. If the beam hits the edge of a bump or the side of a valley, many more electrons are knocked loose and can escape to the detector. The microscope's computer builds the image pixel by pixel. It links the brightness of each pixel on the screen to the number of secondary electrons collected from the corresponding spot on the sample. A spot that produced lots of electrons becomes a bright pixel. A spot that produced few electrons becomes a dark pixel. Because of this, the final image has amazing depth. It looks three-dimensional. Bumps and edges are bright, while pits and flat areas are darker. It's a map of the sample's topography. You can see the intricate alien-looking patterns on a fly's eye. You can see the structure of a pollen grain. You can see the crystalline fracture of a metal. The magnification can be huge, but the real power is in seeing the rich, 3D texture of the microscopic world. It's not a shadow, it's a surface map, painted with electrons, so electrons get us down to the level of atoms. But what if we want to get more personal? What if we want to not just see the shadow of an atom or the bump of a group of atoms, but actually feel a single, individual atom? This requires a completely different approach. No more shooting things at the sample. Instead, we're going to gently touch it. This is the world of scanning probe microscopy. The first of these, and the one that really changed everything, is the scanning tunneling microscope, or STM. The way it works is both simple and deeply weird. It relies on a quantum mechanical effect called tunneling. Imagine you have a record player. It has a turntable and a needle. The needle moves along the grooves of the record to read the music. And STM is a bit like that. It has an incredibly sharp tip, a probe, that is brought very, very close to the surface of a sample. When I say sharp, I mean it. The tip is engineered to be just a single atom at its very end. And when I say close, I mean it. The gap between the tip and the sample might be the width of just a few atoms. The tip does not actually touch the surface. The sample has to be conductive. You apply a small voltage between the tip and the sample. Now, in our everyday world, if two things aren't touching, electricity can't flow between them. There's a gap. But in the quantum world, strange things happen. An electron isn't just a little ball. It's also a wave of probability, and that wave can leak across a tiny gap. There's a small but non-zero chance that an electron on the sample will just appear on the other side of the gap on the tip. This is called quantum tunneling. It's like the electron has tunneled through an energy barrier it shouldn't have been able to cross. This creates a tiny electrical current, the tunneling current. This current is extremely sensitive to distance. If you move the tip just a tiny bit closer to the surface, the current increases dramatically. If you move it a tiny bit farther away, it drops to almost nothing. This sensitivity is the magic of the STM. The microscope is set up with a feedback loop. It tries to keep the tunneling current perfectly constant. To do this, it has to move the tip up and down as it scans across the surface. Imagine the tip scanning over the surface. It approaches an atom, the surface gets a little bit higher, the distance between the tip and the surface shrinks. The tunneling current starts to increase. The feedback loop instantly detects this and pulls the tip back up, away from the surface until the current returns to its set value. Then the tip moves past the atom, the surface drops down, the distance grows, the current plummets. The feedback loop pushes the tip down, closer to the surface, until the current is back to normal. A computer records this up and down motion of the tip. It then uses that data to build a topographical map of the surface. A spot where the tip had to move up is a high point. A spot where the tip had to move down is a low point. The result is a picture of the individual atoms on the surface. You can see them. You can see the orderly rows of atoms in a crystal of silicon or gold. You can see single atoms missing from the pattern, like a missing tile on a floor. It was the first time humanity had ever truly seen individual atoms. We weren't seeing their shadow. We were feeling their shape, one by one, with a single atom finger, and building a picture from that feeling. It's like reading Braille, but for the atomic landscape. The STM is incredible, but it has a big limitation. It only works on materials that conduct electricity. You can't look at a biological cell or a piece of plastic with it because no tunneling current will flow. So, a different tool was invented. It's called the atomic force microscope, or AFM. It works on a similar principle of scanning a sharp tip over a surface, but it doesn't rely on electricity. It relies on pure, simple force. The tip of an AFM is mounted on the end of a tiny, flexible lever called a cantilever. It's like a microscopic diving board. This diving board is so small and light that it can be bent by the incredibly weak forces that exist between atoms. As the tip is scanned across the surface of the sample, it interacts with the atoms of the sample. When the tip gets very close to a surface atom, there's a repulsive force between the electrons of the tip and the electrons of the surface atom. It's like two tiny magnets pushing each other apart. This force, even though it is astronomically weak, is enough to push on the tip and bend the cantilever upwards. As the tip moves into a space between atoms, the force weakens and the cantilever relaxes. So how do you measure this microscopic bending? You can't just look at it. The trick is to shine a laser beam onto the top of the cantilever. The cantilever is shiny, like a mirror. The laser reflects off it and onto a light sensor. When the cantilever is flat, the laser hits the center of the sensor. When the cantilever bends up, the angle of reflection changes, and the laser spot moves up on the sensor. When the cantilever bends down, the spot moves down. The sensor is so sensitive it can detect even the tiniest change in the laser's position. Just like the STM, the AFM uses a feedback loop. It tries to keep the bending of the cantilever constant. As the tip scans over an atom and the cantilever starts to bend, the system pulls the tip up to relieve the force. As the tip moves away from the atom, the system pushes the tip down to maintain the force. A computer records this up and down motion and uses it to create a 3D map of the surface atoms. The AFM is unbelievably versatile. Since it doesn't need a conductive sample, it can be used to see almost anything. You can map the surface of a living cell in a liquid. You can look at the structure of a DNA molecule. You can see the surface of a polymer. You are, in the most literal sense, touching the world at the atomic scale and building a picture from that sense of touch. These methods have taken us from seeing cells to seeing individual atoms. But what about the things inside the atom? What about protons, neutrons, electrons, and the even smaller particles they're made of, like quarks? These things are so small that you can't use a microscope of any kind. You can't touch a quark with a tip. The scale is just too small, and the energies are too high. To see these particles, we have to resort to a much more violent and indirect method. We have to smash things. This is the world of particle accelerators, like the Large Hadron Collider, or LHC, at CERN. The basic idea is simple, even if the execution is mind-bogglingly complex. It's like trying to figure out how a Swiss watch is made, but you're not allowed to open it with a screwdriver. So instead, you take two Swiss watches, smash them together as hard as you can, and then study the bits and pieces that fly out. In a particle accelerator, we take particles, usually protons, and accelerate them to incredible speeds, something like 99.999999% of the speed of light. They race around a huge ring guided by thousands of powerful superconducting magnets. Then, at specific points, the beams are steered into each other. The protons collide head-on. In that collision, an immense amount of energy is released in a tiny point in space. And thanks to Einstein's famous equation, EMC2, the energy can transform into matter. The original protons are annihilated, and a shower of new, exotic, and often unstable particles is created. Things like muons, pions, kaons, and, if you're very lucky, something really heavy and rare like a Higgs boson. These new particles fly out from the collision point in all directions. We can't see them directly. Most of them exist for just a fraction of a billionth of a second before they decay into other, more stable particles. So, how do we see them? We build giant detectors around the collision point. These detectors are some of the most complex machines ever built. They are like giant digital cameras, but they don't take a picture in the normal sense. They are built in layers, like an onion. Each layer is designed to detect a different type of particle or a different property. The inner layers are trackers. They are made of silicon and can detect the path of a charged particle as it flies through. A charged particle leaves a little trail of ionization, and the detector records the position of these trails, allowing a computer to reconstruct the particle's trajectory, its path. The next layers are calorimeters. They are designed to stop particles and measure their energy. There are different types for different particles. An electromagnetic calorimeter measures the energy of electrons and photons. A hadronic calorimeter measures the energy of particles made of quarks, like protons and neutrons. When a high-energy particle slams into a calorimeter, it creates a shower of secondary particles, and the device measures the total energy of this shower. The outermost layers are muon detectors. Muons are like heavy electrons, and they can travel through a lot of material without being stopped. So by the time a particle gets to the outer layers of the detector, if it's still going, it's probably a muon. There are also huge magnets built into the detector. These magnets bend the paths of charged particles. By measuring how much a particle's path curves, physicists can figure out its momentum and whether its charge is positive or negative. So, after a single proton collision, what you have is not a picture. It's a massive flood of electronic data. Millions of data points showing where a path was recorded, how much energy was deposited in a certain location, whether a particle made it to the outer layers. The seeing happens next in the computers. Sophisticated software sifts through this mountain of data and tries to reconstruct what happened. It's a massive logic puzzle. It connects the dots in the tracker to draw the paths of the particles. It links those paths to the blobs of energy in the calorimeters. It uses the laws of physics, like the conservation of energy and momentum, to work backward. If the computer sees a certain amount of energy here in a specific curved track there, and another particle flying off in the opposite direction, it can start to piece together the event. It can say, okay, to get this specific set of debris, a particle with these properties must have been created in the collision and then decayed in this specific way. Finding a new particle like the Higgs boson isn't about seeing a little dot appear on a screen. It's about seeing a statistical bump in the data. You run billions and billions of collisions. You look at all the debris, you find all the events where the debris adds up to a certain total energy. If a new particle exists at that energy, you will see slightly more events at that specific energy than you would expect from random background processes. It's a signal buried in noise. Seeing the Higgs boson means proving, with overwhelming statistical certainty, that this little bump in the data is real and could only have been caused by the decay of this one specific particle. It is the most indirect form of sight imaginable. We never see the particle. We see its ghost, its footprint in the data left behind by its children. And sometimes we see things by their complete absence of interaction. Take neutrinos. They are tiny, almost massless particles that barely interact with anything. Trillions of them are streaming through your body right now from the sun, and you don't feel a thing. 2 is E1. You have to build a truly enormous detector and hope for a 1 in a trillion chance of an interaction. One way is to build a gigantic tank deep underground to shield it from other radiation and fill it with thousands of tons of ultra-pure water. You line the walls of the tank with thousands of incredibly sensitive light detectors. Then you wait. Very, very rarely, a neutrino will happen to strike the nucleus of a water atom. When it does, it can create a charged particle that flies off through the water faster than the speed of light in water. This creates a cone of blue light, a sort of optical shock wave. The light detectors see this tiny, brief flash of light. From the pattern and timing of the flash, scientists can work backward and figure out the energy and direction of the neutrino that caused it. They saw a neutrino not by observing the particle itself, but by observing the faint flash of light it produced in a chance encounter. It's the same with something like dark matter. We've never detected it directly. Is it because of its gravitational effects? We see that galaxies are spinning faster than they should. There isn't enough visible matter to provide the gravity needed to hold them together. So we infer that there must be some other invisible matter providing the extra gravity. We see dark matter by the way it pulls on the things we can see. We see it by the way its immense gravity bends the light from distant galaxies as it passes by, an effect called gravitational lensing. We see its shadow on the structure of the cosmos. So how do we see a particle that's too small to see? The answer is that we change the definition of seeing. It stops being about looking with our eyes. It becomes a process of interaction and detection. We might see the shadow a particle casts in a beam of electrons. We might see the 3D shape of its surface by scanning it with an electron beam. We might feel the bump of a single atom with a microscopic needle. We might see the debris a particle leaves behind when it's smashed to pieces, or we might see the faint ripple it causes in the fabric of the universe. Each step down in size requires a more clever, more indirect method of observation. The seeing is done less by the lens and more by the computer, less by the eye and more by the mind. We build complex machines to act as our senses, translating the rules of the subatomic world into a language of data that we can understand. We may not be able to look at an atom, but we have found a way to draw its picture, to feel its shape, and to read the story written in its heart.